All right, section 1.1 is mathematics and problem solving. Pretty much all of chapter 1, which is 3 sections long, is about different ways of problem solving, but this one has actual problem solving strategies in it. So the first thing we're going to take a look at is the problem solving process. So to solve a problem, we basically run through 4 steps, and you may or may not actually write them all down, but whether you write them down or not, they're the 4 steps you think through when you, or should be thinking through when you're doing a problem. So the first problem is to understand, or the first part of this is to understand the problem. And these are some questions that you might ask yourself as you're trying to understand the problem. Can the problem be stated differently, right? I mean, what is it actually asking for? What is it supposed to be, what am I supposed to be finding? Or what do you need to find what you're asked to find? What are the unknowns? What information do you have given to you in the problem? And then what information, if any, is missing, or what information is not needed? And some curriculums that you use are really heavy on the having extra information to sort through, and some of them aren't. So you have to kind of weigh that out when you're working through problems as well. Second thing you should do after sort of understanding what you're going to be asked to do in the problem is to figure out a plan for solving the problem. And so these are the different problem-solving strategies that I mentioned before. And this is not an exhaustive list. This is just sort of an example of different things you might try. So the first thing is you might look for a pattern in what's going on, right? Like I ate 1 donut today, I ate 2 donuts tomorrow, I ate 3 donuts the next day. What am I going to eat on day 4? There's a pattern, right? You might look for an examine related problem to see if the same technique can be applied. This is exactly what you've done whenever you've gone in a textbook, like back to the examples that somebody supplied, and you look for one. Which one does this look most like? That's what you're doing in that kind of an example. You might look at a simpler or a special case. So maybe you're asked to find something that's true about 10 families, and you're like, okay, what would I do if I only had 3 families? How would I approach the problem? And then sort of generalize that to having more families. You might make a table or a list. And sometimes the table list idea is sort of combined with something else. Like you might do a table or list and something else along with it. But tables and lists are definitely sort of near and dear to my heart because I'm an organizer. And so I like things very organized, so I tend to do tables and lists a lot myself. You might identify a sub-goal. So that means sort of like I need to figure out this piece of information before I can find out the actual result of what's going on. You might make a diagram. Anybody like to draw? Some of you are saying yes, some of you are saying no. You don't have to draw well. I do not draw well. But sometimes a picture will really help. And a lot of times, the age kids that you might be working this kind of content with, a picture works really well because they can see what you're talking about now. So you can be talking about a house, and you're thinking in your mind square or rectangle something, and all of a sudden you realize the child is thinking about the brick building, and that's not what you meant. And so, a picture can sometimes help to establish what you're talking about in a problem solving. Guess and check is okay. That's not a problem. Did you know that? Some people think that that's sort of like cheating. Like I just did it because I sort of figured it out. I guessed the right answer. There's not anything wrong with guessing and checking, but usually the guessing without the checking is unhelpful. So if you're just randomly guessing, that's usually not a helpful thing to do. But if you're guessing sort of in an organized way, strategically, that can actually be a really good way of solving a problem. And then working backwards, I know you've all done this before because working backwards is exactly what happens when you look at the back of the book and say, oh, 18 is the answer, and you say, how did they get that, right? You sort of think through how they could have gotten to that answer. So we do work backwards a lot, and we'll see some examples of ones, some real problems in life that's helpful that way. Occasionally writing an equation. Now, most of the problems we're going to avoid the writing equation, and the reason we are is because this particular content, as it's presented, doesn't need equations. It's not because you couldn't use equations, but it's just not necessary. Equations presume that you know a lot of information about x and variables and solving, and that's usually a little bit higher level thinking, more middle school kind of age, towards the end of elementary, but middle school. And we get into that more actually in elementary math too. So. All right, so after you figure out how you might try and solve the problem, then you actually try and solve the problem. You carry out your plan, whatever it looked like. You implement it. You use precision in your language. You check the steps along the way, either formally, which means like working it out and like putting numbers back into something, or intuitively, like you're saying, does that make sense? Does that reasonable? And then you're keeping a record of your work. Either if it's the picture that you're working with, you're keeping record of the picture. So it's fine to use a scratch piece of paper for like unorganized work, but you should be keeping also organized work as you're going. And then the last thing, the checking your work, oftentimes this is something that we do sort of in our head. You don't have to necessarily show it. Although showing your work as you're checking, it's not a bad thing. But you're trying to decide, there's a couple of things. One is the answer reasonable? I cannot tell you how many times I've taught some kind of an algebra course and somebody tells me that they've got 2.3 babies. No, you don't. There's no 0.3 of a baby or a termite or, whatever, a dog. We don't do decimals with that kind of a content. So that's sort of the reasonableness. Does that make sense? Along the same lines, not just sort of the decimal issue, is does the answer make sense reasonably? That is it too big or too small? Also, if somebody said that they had 52 babies, you might be going, I don't know about that. That doesn't seem reasonable. Maybe not outside of the realm of possible, but not reasonable. So you also just have to check the reasonableness. The last one is the accuracy. Like, does it actually work? So if you did create an equation, if you put the number back in, does it actually satisfy it? Does it actually really work in there in terms of the numerical value? All right, so what we're going to do in the rest of this section, and we won't get very far today, we'll finish up on Wednesday, of course, is we're actually going to work through some of these different strategies, in part because I want you to see how you might sort of look at this and think, oh yeah, this is a really good example of using patterns or whatever. So the first one I've got is a strategy where we use patterns. So let's take a look. This guy's name is Gauss, and Gauss was an actual mathematician, very bright guy, obviously a very bright child as well. So when Gauss was in early grade school, the teacher gave them a problem intending to take them a lot of time. I'm sure you've never had a teacher that's done something like that, right? So this teacher wanted them to add up the numbers from 1 to 100 and tell them what the sum was. So imagine what the most children did. 1 plus 2. They get an answer, and then they plus 3, and they get an answer, and then plus 4, and they get an answer. And this would take a while, right? And this would be a long process. So, like extra points for the teacher for coming up with a problem that should take a long time. Problem is, there's other ways to do it that aren't that sort of just direct, work it out by hand kind of thing like that. So Gauss answered the question almost immediately. I'm sure his teacher was really excited about that. All right? Yes. And so he did it using patterns. So I want to show you how he did it because it's very clever. And it's a really cool tool that can be generalized. And that's what we'll do after that, is to generalize that into a situation that's not numbers 1 through 100. Okay? But here's what he did. So we're going to start out by writing out, sort of beside each other, these numbers 1 to 100. I'm just going to write the first 3. And then I'm going to put dot, 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 and I'm going to write the last 3. So what would the last 3 be? 98, 99, and 100. Now, there's no doubt that this, I think he was 6 if I remember correctly, the 6-year-old is the atypical 6-year-old. But what he did is very clever. What he noticed is that if you put these numbers in pairs, the pairs are going to be the same. So let me show you what I mean. If you take the numbers 1 and 100 and you add them together, what do you get? 101, right. What happens if you take the numbers 2 and 99? You get 101. And then what happens if you take the number 3 and 98? You get 101. And this will always work, right? You pair up the first and last and you sort of work your way in and you get this thing that sort of has this pattern to it, okay? So this is actually the sum, I'm going to call it S, that we're looking for. We're looking for what in the world is this when we add this together. Oh, I have a typo. Nobody wanted to tell me. I'll fix it. 101. That's what it should have said. All right, so this is actually a bunch of 101s added together, isn't it? I mean, really, I've just got a bunch of 101s. The question, of course, then is, well, how many 101s do I have? Well, we'll get to that answer second. But first, what I'm going to do is, instead of just having 1 to 100 list here, I'm going to change every single number to 101. So the 1 becomes 101, the 2 becomes 101, the 3 becomes 101, and then at the end, the 98 becomes 101, the 99 becomes 101, and the 100 becomes 101. They all got bigger, right? Okay, so this is more than I started with, agreed? How much more? It's double. It's exactly double. Do you know why, Allie?
Well, if you're adding them together, you would half it because you already did their half, so.
Right. If we were actually adding them together with how many of them are there total, we would see that these two numbers add to 101, and if I replaced both of them with the number 101, well, then I'd need half as many numbers, right? Because this number 1 and this number 100 both become 101. Two numbers turn into the number 101. So if I replace each one of them with 101, I've doubled the numbers. So you can either write this like this, 2s, or you could write all of these numbers and divide by 2, or times by 1/2. Either of those would be the same equivalent thing. I have a tendency to put the 2s on the other side. That's my default, but you don't have to do that. Now, we still haven't answered the question of how many numbers I have, though. So how many are there? So how many are there? There's 100. Why? I started at 1 and I ended at 100, right? That's 100 numbers. So there are 100 numbers here. Okay, so somewhere in 3rd grade probably, although I'm thinking they do it in 2nd grade now if I have read the curriculum right as they've changed some things along the way, you learn that adding a number to itself a whole bunch of times is a rather unproductive task. I don't want to add 101 plus 101 plus 101 plus 101. And so instead of doing that, there's a shortcut way of doing repeated addition. Do you remember what it's called? It's multiplication, right? I mean, that's the whole point of multiplication, is that I avoid having to do this repeated addition business. So I've still got the double the s, double my sum on the left. And then over here, instead of writing 101 plus 101, I can write 101 times 100 because there are 100 terms. So there are 100 terms added together, and all the terms have the number 101. So I'm going to grab your calculators if you have with you. If you don't, you want to grab your phone real quick just for today, that's fine. Otherwise, bring your calculator next time. No phones after today. But what is 101 times 100? It is. It's 10,100. This particular one doesn't require a lot of calculator. And then what would you do to find out the sum then? You would divide by this number 2, that's the 2s on the right. So we would end up finding that the sum, after we divide the number by 2, that 10,100 divided by 2 gives me what? 5,050. So Gauss told his teacher this number is 5,050. Okay? All right, I know we're out of time. I just want to show you what we're going to do next time is we're going to do the same kind of thing, but what do you see different on this next problem? It doesn't start at 1, right? This one actually starts at 36, and it doesn't end at 100. It ends at 147. So we're going to examine how to use his idea, but in a slightly different case.